Welcome back to the classroom. My name is Mr. Wong. In today's lesson, we are going to talk about momentum, and we're going to also discuss the law of conservation of momentum.
If we look at this diagram here, we talked about it briefly in inquiry 2. When a car is driving into, or when a car is moving, it has kinetic energy. When it collides with the wall, some of that kinetic energy is converted into potential energy. And in this case, it's elastic potential. That elastic potential will bend our car, deform our car, and it might potentially have enough where the car bounces off. So when you see cars colliding and then it bounces off, that's because the kinetic energy is being transformed into potential energy, and then the potential energy is transformed back into kinetic energy where the car moves away. This can occur also where you have some kind of energy transformations elsewhere in the form of heat in collision and also with sound energy, hence why you can hear vehicles colliding together. What we're going to look at today is investigating one-dimensional interactions of objects in a closed system. So in terms of physics, when we mean a closed system, energy shouldn't be lost, so it should be conserved. So we're trying to get rid of outside variables such as, in this case, I'm going to try and get rid of things like we're going to ignore friction. We're going to ignore things like air resistance. If it's in a closed system, we try and ignore these concepts. We're going to also look at the law of conservation of momentum. Okay? So firstly, we should try and define what momentum is, and that's what we're going to look at today. And then we're going to analyze some situations where momentum is conserved in different mechanical interactions. In this word of mechanical, we mean by the collision of the cars. This is your textbook reference if you need to have a look at where to go for information. Back in module 1, when we were looking at kinematics, we were describing motion. So kinematics module 1, that's what we were doing. That's looking at things like distance, displacement, speed, velocity, and acceleration. In module 2, what we're doing right now, part of inquiry 1 and 2, we were looking at what balanced forces does, what net unbalanced forces does. Equilibrium is the object at a constant speed. Was it accelerating or is it stationary? And then we looked at Newton's 3 laws of motion. Now, in the very final one of module 2, inquiry question 3, we're looking at conservation of energy. We looked at that in inquiry 2 as well. We're looking at collisions, that's what we are doing, and energy transformations. Another thing we're also looking at is momentum and a thing called impulse. And this kind of helps us understand and analyze the motion of a moving object a lot better. So let's use a sporting example with playing golf. Now, when the club strikes the ball, we know that Newton's third law of motion is occurring. So the club is exerting a force onto the golf ball, and the golf ball is exerting a force back onto the club. In this case, the club will apply a force to cause the ball to accelerate. This version, it's accelerating to the right. The ball will apply an equal force back to decelerate our club. So that's why our club slows down. If we're talking about in terms of directional vectors, the club is actually experiencing an acceleration towards the left. So we can write it like this. Newton's third law, the ball, let's say, moving towards the right is the positive direction, and in this case, moving left is the negative direction. So this one is going towards the right. This one is now moving towards the left. If we break down Newton's third law, okay, we find that the mass of the ball acceleration equals the negative mass of the club and the acceleration of the club. Okay, what we do know is for acceleration it equals to the final velocity minus the initial over time. So if I substitute this formula into the acceleration, so this goes into here and goes into here, my modified formula will look like this, okay? And there's a reason why I'm going to draw this out like so. If you have a look, our formula is what we established in the previous slide. Now, this time here, the change in time and the change in time here, these are both the same because if the object, when the collision is occurring between the club and the ball, they're occurring at the same time, okay? So if the time's the same thing, they cancel each other out, and I get this formula here, which is the same thing, just no time. Now what we can derive from this is a mathematical formula. So we can say that the change in momentum is related to the object's mass and the object's velocity. So this is momentum, this is the momentum of the club, this is the momentum of the ball. And that's what we come to establish here. That's a really useful equation. So what is exactly momentum? Now, we call momentum an analysis of the object's mass and velocity. So if an object is moving, and obviously the object has mass, it has momentum. Momentum is directly proportional to the mass or the velocity of the object. It is a vector, so you do have to write down the directions at the end of the calculations, okay? As you can see in the second animation down here, in collisions, if it's momentum conserved, you can see that the addups of these two bars here is equal to what was before. So momentum is conserved in a perfect elastic collision. So this is the formula we come up with. If anyone asks you what is momentum, it's just an analysis of a moving mass object and its velocity. The units for momentum is kilograms meters per second. Why is that the case? Because we know that mass is kilograms and velocity is meters per second. In an isolated system, which means we're ignoring air resistance and friction, momentum is always conserved. What do we mean by momentum? We actually mean by the change in momentum. So if two objects collide, okay, then the momentum of these two added together should equal to 0 at the end. So there shouldn't be a change when I look at them again. Okay, Newton's laws. So when Newton came up with his second law, initially it was actually using the concept of momentum. And if I can show you this, this is what the formula looked like at the start. We know that the formula for Newton's second law is mass times acceleration. So how do we get from this back to this here? Well, we know for a fact that acceleration is equal to velocity over time, or you can write it as change in velocity over time as well. So if I substitute A for that, all right, I get the following formula here, okay? And I also know that momentum is equal to mass times the change in velocity. So if I isolate these two equations by themselves and move delta t away from this equation as its own separate fraction, like so here, I can find that the change in momentum over the change in time also equals to the net force experienced by the object. So that's how momentum and force are intertwined with each other. Let's have a look at some calculation questions. So calculate the momentum of a 60 kg student walking east at 3.5. So let's say east is the positive direction. So my mass is equal to 60 times 3.5, and that would be my answer there. In question 2, tomato is 150 grams, traveling at 10 meters per second. Let's also not forget that it is towards the east in this case. So the mass is 0.15. Why do we write that? Because this needs to be converted into kilograms times the velocity here, and that would give us our momentum for question 2 as well. So that's the answer we have for 1 and 2. Let's have a look at question 3 and 4 and 5. So question 3 says we have a car of this mass, has a momentum of so, what is the velocity? Now the best practice is to substitute the numbers in first. So we know the mass, that's there. We know the momentum, which is this number here. So substitute those two. So that's what we have. And now velocity is the thing we want to find. If we want to find velocity, we need to move 750 over to this side, which will be a divide. Okay. So velocity in this case is 15.6 meters per second. Let's look at question 4. The passenger bus is traveling at 80 kilometers per hour. It has a momentum of 1.4 times 10 to the power 4 kilogram meters per second. What's the mass? So we're trying to find m. Again, substitute the numbers in first. We get so. You can see that I've done a conversion here. So in SI units for physics, we're trying to find meters per second for velocity. So 80 divided by 3.6 to make it from kilometers to meters per second. Substitute this over to here, so move that over. I find that the mass of the bus is about 630 kilograms. Question 5, from question 4, so from question 4 up here, the bus has slowed down 90 kilometers to 50 kilometers per hour. What's the change in momentum? So the only way we can calculate change in momentum with the formula we looked at so far is the velocity. So change in velocity equals to final velocity minus initial. Okay, so that's what we have here. Our final velocity was at 50 kilometers per hour. We've converted that into meters per second. 90 kilometers per hour was our initial, and so we've converted that into meters per second as well. What we get is momentum of minus 700 kilograms meters per second. Okay. Negative direction means the object is now moving in the opposite direction. So if it was moving forwards as the positive direction, now that it has a negative value, the momentum of the bus is moving towards the opposite direction, negative direction there. All right, next question. We have a basketball player bounces a ball at 500 grams. Just before it hits the floor, it's moving at 9 meters per second. After it bounces, it leaves the floor at 6 meters per second. So this is actually, we're using this to look at kinetic energy and change in momentum. So in this question, calculate the change in the momentum. Again, we're trying to look at the final velocity and the initial velocity. In this question, it's moving at 9 meters per second, so u is that, and it leaves at that, so that's v there. Okay, so the answer here is minus 1.5 kilograms meters per second, so it's obviously shows that falling in this case was the positive direction for the momentum, and then we could say the negative direction was it bouncing back up. Calculate the kinetic energy of the ball just before it hits the ground. So we're looking at the initial, u equals to 9 in this case. So that's what u is equal to. Substitute it for the mass, which is 500 grams. Remember, this needs to be converted into kilograms, so divide by 1,000. That's why it was 0.5 up here. And then we have 20.25 joules. Trying to find the kinetic energy after it's hit the ground, so we're using the final velocity that we have, and so the value we have is 9 joules here. Okay. In this case, we don't have to worry about whether U is positive or negative. You could say V is technically, you could say V is -6 because it is bouncing back up. But because we're looking at V squared, then -6 squared is the same thing as 36. So it's a positive value there. Does the situation contravene the law of conservation of energy? Now, the numbers might show to you that the energy before and after aren't the same, but that could be because of other issues. So, no, it does not. Some of the energy is being converted from kinetic into sound and heat upon collision on the ground. And also, as it is rising, so if it's rising back up, it's actually gaining potential energy as well. So once it bounces back up, it's gaining potential energy. What we have is conservation of momentum. We're saying that the net momentum of two colliding systems before and after should be constant, so equal to 0. Or we can rewrite it like so. We can also rewrite this as like a little vector quantity, so we can write it like this. Okay, the negative sign here just means the momentum is going in the opposite direction, which makes sense because if these two add up together, they should be equal to 0. All right, let's look at some examples of conservation of momentum. So we have Newton's cradle. So when one of the light bulbs strikes the other, the momentum is carried through the whole system, and it leads to one light bulb being displaced a bit further than the other, and then it comes back and hits the other one. Assuming that there's no friction in the string or the wire, this should be continuously moving in between like so. If you are running and doing your long jump, okay, the momentum you carry while you're running is the thing that you carry over as you start jumping up. The only reason why you stop moving is because that external force of you colliding with the sand becomes the outside force that stops you from moving. You might see other examples of conservation of momentum if you have two objects and bouncing one on top of the other. So the basketball, when it bounces onto the ground, okay, it has momentum of bouncing back up. But if you have the basketball bouncing down, and then you have another, let's say a tennis ball bouncing down with it, okay, as they bounce back up, the basketball doesn't really bounce as much as before as it was by itself. The tennis ball will bounce a lot higher. And the reason being is because the tennis ball is carrying on the momentum of the basketball and being added on towards it as well. So it's carrying the momentum of the basketball and its original momentum of during the bounce, and it bounces higher. The other thing we also know is conservation of rotational momentum. We can see this man here holding a wheel that's spinning. So the wheel is sort of spinning sideways like so. If he holds it in this sort of perpendicular position to his arm, okay, there's no rotation. But if he changes it by 90 degrees, so he swaps that angle by 90 degrees, that causes a angular rotation on this x-axis here, and so the chair also rotates with it. A good example of that is if you have tic-tac and you let it bounce, it'll twist, it'll roll, and then all of a sudden it just jumps up, and that's it showing its conservation of momentum and angular momentum. Angular momentum is just another word for saying rotational momentum here. Okay. Then we have conservation of momentum in sport. You have curling. You can see over here they try and get rid of the friction on the ice to allow for the momentum of the curl to keep moving. So that's really useful. We also have the bowling ball scenario where it causes the spin. And that's also where you can see momentum. In spaceships, the reason why rockets get faster as it is launched into space, that's due to the fuel source. So the fuel source, as it decreases according to momentum, so the momentum of the system should stay the same. So the change in momentum here should stay the same here. So what to compensate, the velocity of the gas is being dispelled a lot faster out. Okay. We also know that if the fuel source is decreasing, the mass of the rocket is also decreasing, which means as well, the velocity of the rocket should also be increasing. So that's why as the rocket goes into space, it is accelerating and going faster and faster. And so like so. Okay, going through some questions of calculation. What is the change in momentum of the book as it is falling? So we have a book that is 1.5 kg and it is falling from a height of 2 meters. We know the formula to find a falling object due to acceleration of gravity is v equals square root of 2gh. So we just substitute those numbers in together and we find the velocity as v equals 6.26 meters per second. What we do know is its momentum is the same before and after. So as it is dropping, okay, its initial momentum here and its final momentum here should be equal but in opposite values. So we can safely say the change in momentum here is 9.39. Okay, change in momentum would also therefore be the negative change there. Okay, so as it's coming down towards the Earth. The speed, what's the change in speed? So when this book collides with the Earth, okay, and bounces back up, some of that momentum from the book is produced on or exerted onto the planet. So what speed change has occurred? We can calculate that with the mass of the Earth. You can find this on the HSC physics data sheet on Google, and they'll give you the certain values you're looking for. 2019 is the way to go. And so the change in velocity would be equal to minus 1.57 times 10 to the power 24 meters per second. So every time you're jumping on the Earth, you are actually transferring your momentum on the Earth and you are changing the velocity of the Earth at some degree. But because you are very small compared to the Earth, whatever collision you do cause, it won't be very significant. Okay. And also change in momentum if you have two objects colliding with each other. Okay, so they collide with each other. Momentarily, when they bind with each other, you could say their masses combine together, and we'll look at that in terms of collision types. But what will happen is they will separate from each other eventually, and they might transfer their momentum towards each other. So block A might transfer some of its momenta to block B, and block B will transfer some of its momenta back to block A, vice versa. And so let's using this as a final example. So the law of conservation of momentum states that provided we don't have any external forces, okay, on the system, so no friction, no air resistance, the total momentum of the system before and after the reaction is the same. So we can rewrite this at that. So the sum of the initial and the sum of the final, let's say if it's two objects colliding with each other, A and B colliding, the final momenta of these two added together will still be the same. And we can rewrite it as this equation here. Okay, and let's go through this last little question before we end this lesson. So if we have a look, if two objects, so we're saying determine the final velocity of B in block A if it rebounds. So if it's rebounding, we have two similar objects coming back out. So mass of A and mass of A before and after should be the same. Same with B. We know what the velocities are, and so we can substitute this in. You'll notice that some of the velocities are negative. So you can see here we have -4, we have -0.5. Now the main difference is their direction. So if we're saying towards the right is the positive direction, then we're saying any motion in the negative direction is or left is the negative direction. Substitute these numbers in together, you'll find that it's 8 equals to minus 2.5 times plus 3 VB. And you'll find that the overall velocity is 3.5 positive, which means B is going to the right, or in the right in this case. B, what if they combine, so they collide together and combine in one go? Then we can add the two masses together, okay? And combine them together like so. And so we find that if they combine together, the final velocity of this massive double block object is 1 meters per second.
And that concludes our lesson for today. We talked about momentum, how it is the product of mass and velocity. We also talked about the conservation of momentum and how during a collision, how that is actually conserved. If you found this video interesting, like, subscribe, and I will see you next time.